Hi, I'm Professor Melko, Chemistry PhD, and today we're going to talk about gases and the variables that affect gas pressure, like temperature, volume, and number of molecules. Now, gases are probably the state of matter that's hardest to visualize because, well, we can't see them. So the question comes up, are gases even real? Yeah, they're definitely real. I'm here to share the truth with you. So let's jump into the lecture. So what is a gas? Gases have a variable shape and volume. Okay, so we know this if you push on the side of a container, for instance, like you might have a piston assembly that looks something like this. And inside this piston assembly, there are gas molecules, and those gas molecules are taking up the space inside the piston. Now, if I move this top of the piston down and compress the gas, they compress uniformly, right? All the gases move down together to occupy this smaller volume now. Okay, so clearly the shape and the volume is variable. The opposite is true for solids. If this was completely filled with a solid and not a gas, it wouldn't really compress and the volume would not be variable. The opposite is true, of course. I can expand this gas and it'll expand uniformly just like it compresses uniformly. Usually these gases have a low density, right? The molecules here are pretty far apart from one another compared to a solid where the atoms are stacked right on top of each other. Okay, so this would be a solid. That's not what's going on here. Gases have a much lower density, right? The atoms and the molecules are spaced further apart. Now, when I introduce one gas to another, they mix pretty uniformly with any other gases in the container, right? Whereas if I put a solid gold bar next to a piece of solid lead, the atoms don't start spontaneously mixing, right? But gases sort of expand to take up a volume, and so the gases of two different compounds, like nitrogen and oxygen, will spontaneously mix. So these are some properties of gases that make it a little bit unique in terms of how we need to think about them with regard to solids and liquids. Now, one telltale sign that we have a gas is the pressure that we measure, okay, in a given volume, right? And pressure is really a force over an area. But within this office that I'm sitting in, there is a pressure being exerted right now on me by the gas molecules in this room. And pressure, back to a physics definition, is force divided by area. So sometimes we just see F over A. Okay? Any force over an area creates a pressure, right? There's pressure of me, pressing on my forehead. I feel that pressure. I feel that force that's being exerted over the certain area. Okay? Gas pressure is similar. It's just here the pressure is this molecule slamming into a wall. And the force created when this molecule hits the wall and the area over which the molecule is impacting the wall. Okay? So this molecule is creating a force over an area or a pressure. And so we sum up what all the molecules in the room are doing over the extent of the area of said wall, and we get that total gas pressure that exists in the room, for instance. Okay? Now the pressure is going to depend on, obviously, this force, right? How fast are the molecules moving? How much energy do they have? That's going to have to do with the temperature, right? So as the temperature goes up and these molecules move faster, they might exert more of a force because they're impacting the wall with more force. So it's not just going to be temperature, though. It's going to be the number of molecules as well that is affecting the gas pressure. The more molecules there are, right, the more of these impacts there are and the higher the pressure. Okay. As it says here, if the temperature of the gas increases, molecules move faster, striking the walls with more force. Also, they're going to strike more frequently, right? If this molecule is moving around this box faster, it collides with the edges of the box more frequently. And so there's more pressure being exerted because there's more of these impacts, more of these forces over the same area. Okay, so this is what gas pressure is. It's this force that the gas molecules are exerting on something. Now, atmospheric pressure, right, is the gas that is part of Earth's atmosphere that's exerting a pressure on everything, right? Even you sitting there have these gas molecules impacting on the outside of your body and creating a force. So the air molecules in our atmosphere exert a force on all objects. And we call this the atmospheric pressure. We have an instrument used to measure this pressure, and it's known as a barometer. Just like temperature is measured with a thermometer, right? Pressure where the unit of pressure, 1 unit of pressure, is a bar. So this is measuring the bar or the pressure that is created. So a barometer measures pressure, a thermometer, right, measures temperature. Barometer works like this. At least in the old days, we used to have these mercury barometers, right, where the pressure of the gas molecules hitting the surface of this, right, would push some of the mercury up into this tube. And the height measured here of the mercury became this pressure. And we saw that as we took this instrument up on mountains, the height lowered, the pressure was less, right? At sea level, this height of mercury corresponds to about 760 millimeters. Okay, that is the height of the mercury. And so this becomes a unit of pressure, and we call this 1 atmosphere. At sea level, the molecules in our atmosphere exert a pressure to raise the mercury up 760 millimeters. And so this 760 millimeters mercury, that is now a unit of pressure. That is how we measure pressure. Okay, but we also measure it using the unit atmosphere. And it turns out there's a bunch of different units, and here's how they are all related to one another. This 1 atmosphere was first defined by this height mercury rose. You can turn this into not millimeters but inches using a conversion. You can turn this into something called torr, or pounds per square inch, or kilopascal, just a bunch of different units of pressure. Much like we have Fahrenheit, Celsius, and Kelvin for temperature, we have different units for pressure. And so the point is, all of these units are equivalent to one another. 1 atmosphere equals 760 millimeters of mercury. 1 atmosphere equals 14.7 pounds per square inch, equals 760 torr. So you might have to do some conversions between these various units, and that's what we're going to get some practice with now. So feel free to pause the video here and try this problem before you watch me solve it. As always in these conversion problems, I'm going to write the unit that I'm given, 26.2 inches of mercury. I'm going to write that just like this, IN period Hg for mercury, and I want the pressure in atmospheres. I'm going to set up a basic dimensional analysis. Whatever unit I'm given here, I place down here. Whatever unit I want to go to, I place up here. And now I need the numbers to go with these units, so I consult this table. I see that there's 29.9 inches of mercury, so I write 29.9 next to the unit that I know has to cancel here. And I write 1.00 next to atmosphere. And now my conversion is complete, and I can do the math. 26.2 divided by 29.9, and I get 0.876 atmospheres. Okay, so this is an example of a pressure conversion. Now, I've already briefly discussed the variables that affect gas pressure, but I want to build more of a conceptual understanding now of how this works. Okay, there are really 3 variables we're going to talk about in this lecture that affect gas pressure. One is the volume of the container, the other is the temperature, and the third is the number of gas molecules, or the amount of gas. So let's think about volume first. Okay, if I have this container that looks like this, and there's 3 molecules in it, the pressure has to do with how many times, or I should say how often, these molecules are hitting the edges, right? Because when they hit the edge, they're exerting a force over the area that they're impacting, and that is pressure, right? Pressure is force over area. Now, if I decrease this volume, and now the box is decreased volume, and now the box is only this big, and the molecules are moving with the same energy and the same speed, it's pretty easy to see they're going to hit the sides of the box more often. And so if they're hitting the edges more often, there's going to be more collisions with the wall. And so this force will be exerted more often, and pressure is force over area. So as the force goes up, the pressure goes up. So as the volume goes down, okay, pressure goes up. And so we say pressure and volume are inversely related. The opposite is true, of course, if I take this volume and make it much bigger. Right, well, now these molecules have to travel quite a long way before they hit the wall. The collisions are less often. As volume goes up, then pressure will go down. Okay, so that's pretty easy to visualize why volume is related to pressure. Another factor, another variable that affects gas pressure is the temperature. Okay, so imagine we still have this box. Here we're not going to change the volume of the box. We're going to assume for all intents and purposes that these are the exact same volume. Call it V1. Both these boxes have the same volume. Okay, but they have different temperatures. Okay, and we're going to say temperature 1 is higher than temperature 2. Right? So maybe I still have 3 molecules in here, but these really have a lot of energy. Right? They're zooming around really fast. Whereas these molecules over here have a lower temperature, and they're kind of slowly meandering towards the wall. Okay, it's easy to see then at this lower temperature, the molecules don't hit the edges as often, right? Less frequent collisions with the wall. And they're also hitting the wall with less force, right? So remember, pressure is force over area. So if this force is lower because the molecules are moving slower, and it's less often, both of those factors decrease the pressure. Okay, so as the temperature drops here, the pressure also drops, and vice versa. As the temperature goes up, the molecules move faster, they hit the walls more frequently, and with more force, which raises the pressure. So we say pressure and temperature are directly related. That is, as temperature goes down, pressure goes down. As temperature goes up, pressure goes up. So that's volume and temperature and how they affect gas pressure. But what about the number of molecules? Well, let's do the same exercise. On the left and on the right, these two boxes assume they have the exact same volume. And now let's also assume they have the exact same temperature. I've prepared them to be identical. Maybe on the left I have 3 molecules. Maybe on the right I have 1. Okay? So I would say the number of molecules N, 1, and the number of molecules of N, 2. N1 is greater than N2. 3 is greater than 1 molecule. Well, you could probably guess at this point that 3 molecules impacting is going to have a higher pressure than 1 molecule impacting, right? So the pressure over here when there's 3 times the molecules is going to be much higher. There's more collisions, more force, more pressure, as opposed to just 1 molecule exerting a force. Okay, so as the number of molecules goes up, the pressure goes up. As the number of molecules goes down, the pressure goes down. Okay, so pressure and number of molecules are directly related, just like pressure and temperature are directly related. Volume and pressure are inversely related. That's what we've talked about thus far. Let's stop here and try this practice problem. A container has 0.250 moles of gas. Which of the following results in a decrease in the pressure of the gas? Take 30 seconds and try to answer for yourself. Okay, so 0.25 moles, let's just draw some gas molecules in here. If I add more gas, the pressure is going to go up. So it clearly can't be A. If I have this much gas and they're moving at some speed, and I heat the gas and I make them go faster, that's going to be a increase in force or an increase in pressure. That one can't be right either. Doubling the container size. If I have these molecules, they're hitting the edges with some force. If I make this twice as the size, these 3 molecules have to go much further to reach the edge of the container it takes them longer before they exert this force. They're not exerting as many forces as often. So here the pressure should in fact decrease by doubling the container size. The answer here should be C. I think that'll do it for this lecture. We're going to, in the next lecture, quantify exactly how the pressure is affected as I change the temperature or the volume, okay, or the number of molecules, and get into some laws of gases like Boyle's and Charles and Lusak's law. Okay, so that'll do it for this lecture. As always, please feel free to like and subscribe to this channel on YouTube, or check me out over on Twitch, where I do weekly office hours answering whatever chemistry questions you might have. That'll do it for today's lecture. See you next time.